Good morning, students. Myself, Vijay Shankar from EC Department at Chevrolet Engineering College. Today, we are going to discuss about the last topic in signals and systems. That is a 5th unit, Laplace transform and the Z transformation. The first part is a Laplace transform. See, previously, the last second unit and the third unit, we already discussed about the Fourier transformation and the Fourier series. The Fourier transformation and the Fourier series is both are converting the time domain to the frequency domain, and the Laplace transformation also the converting of time domain to the frequency domain as in the analog form of the continuous time functions. And the last part the second part in the 5th unit is the transformation is also the transformation only. The time domain is converted into the frequency domain. The time is not the continuous time, it is a discrete time function. X of n is converted into the frequency, the x of z. In the Fourier series, the x of t is converted to the x of k. In the Fourier transformation, x of t, the time domain is converted to the frequency x of omega. In this function, the Laplace transformation also converting the time domain x of t into the frequency domain is the x of s. Okay, that is a first part in the 5th unit, the last unit. Okay, my dear students. So let us start the Laplace transformation. So the first one, the Laplace transform is another mathematical tool. The Laplace transform is another mathematical tool for analysis of signals and the systems. The Laplace transform is another mathematical tool used for analysis of signals and the systems. Laplace transform provides border characterization of signals and the systems compared to the Fourier transform. The Laplace transform can be used for analysis of unstable systems where Fourier transform has limitations. There are two types of Laplace transform: bilateral, nothing but the two-sided Laplace transform, and second one is a unilateral, nothing but the single-sided Laplace transform. Bilateral and unilateral. So both are the same. At one property only there is a difference of bilateral and the unilateral. Remaining is all it is similar to that of bilateral and the unilateral. So only simple definition saying it is a unilateral is for positive real axis. Bilateral means including the negative real axis also. Minus infinite to the 0 and 0 to infinite, there is a two-sided, left-sided and the right-sided. Two-sided, it is from minus infinite to infinite means bilateral, we can call it as. Unilateral, we can take only from the 0 to infinite. Only the positive real axis. Okay. The Laplace transform is another mathematical tool used for analysis of signals and systems and provides a border characterization of signals and the systems compared to the Fourier transformation. The Laplace transform is used for analysis of unstable, and the Fourier transform has some limitations. There is two types of Laplace transformations, bilateral and unilateral. And the definition of the Laplace transformation, the bilateral Laplace transformation definition is f of s is equal to s. Still now, we learn the Fourier transformation. We learn the Fourier transformation is x of omega in the frequency, x of k, Fourier series, x of k is a Fourier series, x of omega is a Fourier transformation. Now it is a x of s, Laplace transformation, s value. Okay, x only. Here I am taking the inside, there is f of t. So what is the definition saying that x of s is equal to, since it is a bilateral, the limitations is from minus infinite to infinite, converting of a time domain function, the signal x of t, e power minus s t dt. Here inside I am taking the f of t, so the frequency is the f of s. Here the integration is taken from minus to the plus infinite, hence it is called bilateral or two-sided Laplace transform. Bilateral or two-sided because of plus infinite and the minus infinite varies from minus infinite to 0 and 0 to infinite at the origin. So it is a single left-sided and this one is a right-sided. Both we can call it as a bilateral or two-sided Laplace transformation. Here f of t is a time domain signal, f of s is a Laplace transform. F of s or x of s. And if we take the signal x of t, the time domain signal, f of s, x of s, x of t, Fourier transformation. First we are taking the Fourier series, x of k, x of t, the time domain function, apply the Fourier transformation, x of omega. Now I am taking the x of t as a Laplace transformation, x of s. Got it, my students? It is a definition of the Laplace transformation. Definition of the bilateral, here the integration 2 times they get definition, and the unilateral Laplace transform is given as unilateral Laplace transform is given as, it is a repeated, my dear students, there is no anything here. Unilateral Laplace transformation is given as from 0 minus to infinite. What is the 0 minus? The new term we are hearing here, 0 minus and the 0 plus. Both are the same, equal to 0 only. 0 plus is a just above the 0, 0 minus is a just below the 0. Alright. 0 is there, 0 minus just below the 0, before the 0 here. 0 plus is just above the 0. Both, all the 0 minus and 0 plus is both of the zeros only. Okay. F of s is equal to one-sided only, one-sided from 0 minus to the infinite, f of t e power minus s t dt. Here observe that the integration is taken from 0 to infinite. The unilateral Laplace transform is mainly used for analysis of causal signals. The lower limit is taken as a 0 minus. This is to include the time just before the 0. Just before the 0. What they are saying, it is just before the 0. It can be taken as 0 plus also. It can be taken as 0 plus also. For continuous time function, f of 0 minus is equal to f of 0 plus. Both are is the same. Thus, for continuous function, the integration is effectively taken from 0 to infinite. Since the value of f of t is just before and after the 0 is the same. See what they are saying here, even it is denoted as a 0 minus. For continuous time function, the integration is effectively taken from the 0 to infinite. Since the value is f of t is just below and after the 0 is the same. The f of t and f of s is called Laplace transform pair. Laplace transform pair. Got it, my students? Now it can be written as f of t Laplace transform f of t, the Laplace transform f of s. The variable s is a complex frequency. f of s, f of omega, f of k, all it is a frequency only. But here the f of s is a complex frequency and it is given as s is equal to sigma plus j omega. What is the sigma here? Sigma is a real axis, j omega is a imaginary axis, is a s-plane, a plane S-plane having the 4 quadrants. From 0 to the infinite is a one-sided, minus infinite to 0 is a another sided. So bilateral is totally common as a bilateral Laplace transform. And only if I am taking the single sided is a unilateral signal. What is that S? S is nothing but having the sigma plus j omega is a complex frequency. The real term is a sigma and imaginary term is a omega. Alright, now I can substitute in the definition of the Laplace transformation. F of s is equal to integral minus infinite to infinite f of t e power minus sigma plus j omega into t dt. Expand this e power minus is a 2 terms, e power minus sigma into t, e power minus j omega t dt. Got it, my students? And the f of s is equal to integral minus infinite to infinite. Take as a single term, f of t e power minus sigma into t, e power minus j omega t dt. The above equation shows f of s is basically the Fourier transform, basically the Fourier transformation of f of t into e power minus sigma into t. This is a relation between of Laplace and the Fourier transform. How it is? What is the Fourier transformation formula? X of omega is equal to integral minus infinite to infinite x of t e power minus j omega t dt. Got it, my students? Now, what is the Fourier transformation? Not the Fourier, Laplace transformation definition. X of s is equal to integral minus infinite to infinite x of t e power minus st dt. So what is the s here? The j omega only. But saying that the s having s-plane with a real term and the imaginary term, you can substitute here minus infinite to infinite x of t e power s is a sigma plus j omega t, j omega into t dt. I substituted the s is equal to sigma plus j omega. After splitting the exponential value, x of t into e power minus sigma into t as a one function, e power minus j omega t dt. So now you can observe here the Laplace transformation and the Fourier transformation is both are the same. Instead of x of t, here it is x of t into e power minus sigma into t. Is a Fourier transformation function only. When it becomes a Fourier transformation, sigma is equal to 0. When sigma is equal to 0, e power 0 is a 1. When sigma is equal to 0, now it becomes of minus infinite to infinite x of t e power minus j omega t dt as of the Fourier transformation definition when sigma is equal to 0 in this equation. Or otherwise you can say x of t e power minus sigma into t is a Fourier transformation only. Not only here explain that the above equation shows f of s is basically the Fourier transform of f of t e power sigma into t. So it's totally, if assuming a one signal, x of t, that signal is x of t e power minus j omega t dt is nothing but x of omega. What did my students? When it is equal to the x of omega, when the sigma is equal to 0, f of s is equal to x of omega. The Fourier transformation, it becomes of Laplace transformation becomes a Fourier transformation by substituting the sigma is equal to 0. Okay, this is the relation between of Laplace and the Fourier transform. The Fourier transform is given by the above equation must exist, which is actually the Laplace transform. Hence, sufficient condition for f of t to be the Laplace transform is that is definitely less than the infinite function for real and the positive values of sigma. For the real and the positive values of the sigma. Got it, my dear students? The next one is inverse Laplace transform. We know the x of omega is equal to is a Fourier transformation, integral minus infinite to infinite, x of t e power minus j omega t dt as a Fourier transformation. What is the inverse Fourier transformation? Here the x of t is equal to integral minus infinite to infinite. Now the x of omega as an input, and negative exponential becomes a positive exponential e power j omega t with respect to the frequency we are applying. Because it's a x of omega, signal is a frequency. Signal is a time domain, we can apply the integral with respect to the time only. Signal is a frequency, you can apply the integration with respect to the frequency. And 1 by 2 pi also. 1 by 2 pi. Now the Laplace transformation definition saying that x of s is equal to integral minus infinite to infinite x of t e power minus st dt. The definition of Laplace. And the definition of inverse Laplace transformation. What is the inverse? Here the x of t becomes now the output. X of t is equal to. And now it is a complex frequency. Complex frequency means 1 by the 2 pi j. And the integral is from sigma minus j infinite and sigma plus j infinite. Because it is a complex and the sum function, x of s and e power, here the negative exponential, we are taking the positive exponential and with respect to the s frequency. Only the difference, the inverse Fourier transformation as usual, the inverse Laplace transformation also. But the s is a complex frequency, 1 by 2 pi j, and the limitations also as of sigma minus j infinite to sigma plus j infinite. The definition of inverse Laplace transformation. In terms of f of t and f of s, as I wrote here, the x of t and x of s is a variable only. F of t is equal to 1 by 2 pi j, the integral is sigma minus j infinite and sigma plus j infinite f of s e power st into ds. Got it? Now, enter the very important topic, the Laplace transformation properties. Previously, what we discussed about the properties, every time I said all the properties what we have in the Fourier series, in the Fourier transformation is also the same. 9 properties. The name is also the same. And similar transformation as a linearity, shifting property, frequency shift, convolution, and the differentiation, integration, the duality properties for the Fourier transformation, and integration properties there in the Fourier transformation only. Okay, these are some properties what we have learn in the Fourier series and the Fourier transformation. Only the definition is changed. The concept is the same. Only the definition, nothing but the mathematical expression for the Fourier series, Fourier transform, and the Laplace transformation is different, but the properties concept is the same. You have to prove the same way by using the definitions of the Laplace transformation here itself, what we did in the properties for Fourier transformation and the Fourier series also. Okay. Linearity property, time shift property, frequency shift property, differentiation property, and the convolution property, modulation property, integration property, Parseval's theorem. Got it, my student? These are the different properties we already learned in the Fourier transformation and the Fourier series. Now, the similar names what we have in the Fourier transformation and the Fourier series, here also the same. First one is a linearity property only. What is a linearity property? Saying that statement is f1 of t is the Laplace transformation of f1 of s, and f2 of t, the Laplace transformation is f2 of s. Be the Laplace, two Laplace transform pairs, then the linearity property states that the Laplace transformation of a1 f1 of t plus a2 f2 of t, a1 f1 of t plus a2 f2 of t is equal to a1 f1 of s, a2 f2 of s. Here a1 and a2 are the constants. Same equations in the Fourier transformation and the Fourier series also. The input is the same, a1 x1 of t plus a2 x2 of t. But in the frequency, Fourier series means x1 of k and x2 of k. Fourier transformation is f1 of omega and f2 of omega. Now, in the Laplace transformation, the change is a variable here itself for the within the parentheses, a1 f1 of s and a2 f2 of s. Here a1 and a2 are the constants. The proof, let the Laplace transformation of a1 f1 of t plus a2 f2 of t as an input signal. According to the definition of Laplace transformation, integral, it is not the 0 minus, my students, it's a minus infinite only. The properties what we are taking here, all the properties for the bilateral only, not for the unilateral Laplace transformations. Bilateral, remember that one, minus infinite to infinite, f of t into e power minus st dt. What is f of t here? a1 f1 of t plus a2 f2 of t e power minus st dt. Split the two parts. a1 integral, it is a minus infinite, my students. Minus infinite. So integral minus infinite f1 of t e power minus st dt is also the definition of the Laplace transformation. Since it is a signal is f1 of t, you can write it as in frequency f1 of s. The second term also f2 of s. Got it? The linearity property. Coming to the second shifting theorem or translation in time domain. Shifting in time domain or time shift property. Simply saying. Shifting theorem in the Laplace transformation. Remember, and you have to, if you answer in the external examination, which property is asking, you have to see that linearity means don't write it is for Fourier series and the Fourier transformation. For which transformation they are asking the linearity? For which transformation they are asking for the time shift? That is a very important. So if you know that, but for which it is asking, they are asking for the Laplace transformation, you have to prove by using the Laplace transformation definition. The time shift property, they are asking for the Fourier transformation means by using the definition of Fourier transformation, you have to prove the time shift property. That is a very important matter, students. Shifting theorem or the translation in time domain or time shift property. Time shift property. So what is the statement here? Let f of t is a Fourier transform, the Laplace transformation f of s be the Laplace transformation pair if f of t is delayed by the time t naught. If f of t is delayed by time t naught, then its Laplace transform is multiplied by e power minus s into t naught. E power minus s into t naught. That is, the Laplace transformation f of t minus t naught is equal to e power minus s t naught into f of s. Okay, I will explain here itself. Second property, shifting theorem. Shifting theorem for the Laplace transformation. Okay, what is the definition saying that the Laplace transformation of x of t minus t naught is equal to e power minus s into t naught x of s. Okay, now you can see the proof. According to the definition of Laplace transformation, x of s is equal to integral minus infinite to infinite x of t e power minus st dt. What is the x of t given here? The take that is x of t minus t naught. Integral minus infinite to infinite x of t minus t naught e power minus st dt. The input is shifted with the t naught samples. Let t minus t naught is equal to some p, and t is equal to p plus t naught. Okay, my dear students. And now, and the t is a variable and the p is also variable. T naught is a constant because it is a shifted samples only. The dt is equal to, apply the derivative, dt is equal to d into p. Substitute here, minus infinite to infinite x of p e power minus s into, what is the t value? P plus t naught into d suffix b, or the suffix dp, as a dt is equal to dp. Integral minus infinite to infinite x of p e power minus s into p dp and e power minus s into t naught. So this equation C is a Laplace transformation definition only. Laplace transformation definition only. X of s is equal to x of s into e power minus s into t naught. So don't think that is a x of s is equal to x of s and don't cancel this one. X of s is nothing but here you have to take the Laplace transformation of x of t minus t naught. So directly I substitute the x of t minus t naught there. Understood? So actually it is x of t only. X of t Laplace transformation is equal to, as I am substituting the x of t here. The second equation, the Laplace transformation of x of t minus t naught. Now I substitute instead of x of t here, the x of t minus t naught. Finally, we got the x of s e power minus s into t naught. Similar in the time shift property, what we learn in the Fourier transformation. What is the Fourier transformation? The x of t minus t naught Fourier transformation is e power minus j omega into t naught x of omega. Instead of j omega, here it is s only. Okay, and the omega is yes. Change of omega as the s value becomes of Laplace transformation. Okay. Now, you see here they have Laplace transformation of f minus t naught. It is don't take it is a 0 minus students. It's a bilateral only. Don't write it is a unilateral. Bilateral minus infinite to infinite. So e power minus s into t naught into f of s. Got it? Now the third property, frequency domain. Nothing but it's a frequency shift property. Complex translation or translation in frequency domain. Or it is also the frequency shift in the Laplace transformation. What is the frequency shift here? S minus A. S minus A with the Laplace transformation of e power at into f of t. E power a into t f of t. Okay, instead of a as here I am taking the a value. What we got in the time domain, time shift property. Time shift property saying that t minus t naught, there is a sample is shifted in the time domain. Frequency domain is multiplied with the negative exponential with s into t naught. But now there is a change is s here. Frequency is changes. Frequency is shifted with the a samples. So a, and there is no any change in the time, the t f of t. So for the time domain signal f of t is multiplied with the positive exponential of e power at. Applying the Laplace transformation for this signal, you got the shifting occurs in the frequency. F minus SCA, f of S minus E. Okay. Now see the third property. Translation in the frequency or shifting in the frequency domain. As a statement saying that the Laplace transformation of e power at x of t. I'm taking the x, they are explaining in the f terms, f signals. X of t is equal to e power a into t, not the a into t, sorry. Frequency is shifted with s minus a. Okay. I'll take the proof here. What is the definition saying? The Laplace transformation of x of t is equal to integral minus infinite to infinite x of t e power minus st dt. What instead of x of t, I'm taking that e power at x of t is equal to integral minus infinite to infinite. Substitute that is a e power at x of t. As a signal here, e power minus st dt. That is equal to integral minus infinite to infinite x of t e power. Take the common as a t value here, s minus a into t. Here I am substituting the minus into dt. So now observe here, it is also similar to that of Laplace transformation definition only. Compare these two. It is equal to x of s, but here instead of s minus a. So it becomes of, so I wrote here not the f, x. Okay, because I take the signal is x of t. X of s minus a. Therefore, e power at x of t, the Laplace transformation of you get the x of s minus a. What it minus terms? There is a frequency shifted with a samples. Exponential, positive exponential is multiplied to the time domain function. But time domain is shifted with the t0 samples. Frequency domain signal is multiplied with the negative exponential with that sample t0, e power minus s into t0. What it minus friends? So what is here? I'm saying that is a x of t minus t0. The Laplace transformation is e power minus s into t0 x of s. Observe here. These two are the is time shift. Means input is shifted with the t0 samples. Negative exponential is multiplied and the t becomes of t0. And here the frequency is shifted with the a samples. The time domain signal is multiplied with the positive exponential and s is becomes a here. S is becomes a. The t is t0 samples we shifted there is t0. And the frequency shifted with the a samples means the frequency value x s is changes as a into t x of t. Okay. Now, third example, same thing. Complex translation or the translation in frequency domain as e power at f of t, e power at f of t, e power minus s t dt, f of t into e power minus, you can take as a common, s minus a into t. As the definition of Laplace transformation, it is f of s, but instead of s here, s minus a. Okay. Second property, first property is a linearity property, same as in the Fourier series and the Fourier transformation. Time shift property is also the same as Fourier transformation and the Fourier series. Third property also the frequency shift property, or it is also called as complex translation or translation in frequency domain. And shifting theorem, translation in time domain. All the three properties we have in the Fourier series and the Fourier transformation also.